Welcome to the lecture series on CFD Part 1. This is lecture 16 on Introduction to Solution Methods for the Navier-Stokes equations. This lecture is about special features of the Navier-Stokes equations which go beyond the generic conservation equation that was considered so far. In preceding lectures, we assumed that the velocity field was known, which is what we normally do when solving scalar transport equations. Now we need to compute the velocity field and must deal with the non-linearity of convection terms in the momentum equations. Viscous terms in the momentum equations are also more complex than diffusion terms in the scalar transport equation, and discretization of pressure terms requires special attention. Such terms are not present in the scalar transport equation. In addition to momentum conservation, we should also try to conserve the kinetic energy, but there is no independent equation for kinetic energy. It is also not obvious how to compute the pressure in an incompressible flow. It will be shown how a differential equation for pressure can be derived, but it is seldom used because of difficulties with boundary conditions. The initial and especially the boundary conditions for the Navier-Stokes equations require also special attention, in particular the conditions at solid walls and symmetry planes. In preceding lectures, we have dealt with a conservation equation for a generic scalar variable. The discretization principles described so far apply also to the conservation equations for mass and momentum, which are collectively called the Navier-Stokes equations. The left-hand side of these equations, that is the rate of change in the convection term, looks the same as in the generic transport equation. However, the right-hand side differs. Let us first have a look at the integral form of the Navier-Stokes equations. The mass conservation equation, which is also called the continuity equation, has no terms on the right-hand side when only incompressible flows are considered, which is the case for the time being. The momentum equations, shown here for the velocity component ui, have on the right-hand side surface and body forces. We shall for the time being consider only viscous stresses tau ij and pressure forces under the surface integral, and a generic body force bi under the volume integral. The Navier-Stokes equations for incompressible flow are shown here in differential form and tensor notation. By comparing these equations with the generic scalar transport equation shown in slide 15 of lecture 3, we can identify the following features of the Navier-Stokes equations which require special attention. Because the momentum is a vector quantity, there are many options for the choice of variables, that is velocity components, and their arrangement on the grid. The diffusion terms are more complex than in the generic scalar transport equation. The momentum equations contain pressure terms which have no counterpart in the generic transport equation. And the continuity equation does not have a dominant variable in incompressible flows, and it is not obvious how to compute the pressure. We shall discuss these features in the following slides. The convection terms in the momentum equations look the same as in the generic transport equation when phi is replaced by the velocity components ui. As indicated in lecture 6 and 9, these terms are usually linearized using Picard iteration approach, that is, taking the mass flux from the previous iteration and treating it as known. It is often said that ui is the convected velocity component, while uj contributes to the convecting mass flux. Discretization of convection terms follows principles described in lectures 4 and 5 for finite difference methods, and in lectures 7 and 8 for finite volume methods. The viscous stresses in momentum equations are analogous to the diffusion flux in the generic scalar transport equation. However, because the velocity is a vector quantity, instead of a simple flux vector equal to the product of diffusivity gamma and the gradient of scalar phi, we have in the momentum equation a product of dynamic viscosity and the rate of strain tensor. How are these extra terms treated is described in the next slide. One part of viscous stress terms is equivalent to the diffusion term in the generic transport equation and can be discretized in the same way as shown by these expressions. The remaining part is, in finite volume methods, of a similar magnitude on any single control volume phase. However, its integral over a closed control volume surface is identically zero in the case of incompressible fluid and a constant viscosity. Analogously, in the differential form of equations, we can take the viscosity out of the derivative and then reverse the order of differentiation, which leaves the continuity equation, that is, the divergence of the velocity vector, inside brackets, which is under those conditions equal to zero. When the viscosity is not constant, the extra terms create a non-zero net effect, but it is much smaller than the net effect of the other part of the stress tensor. For this reason, this part, given by these expressions, is computed explicitly using values from the preceding iteration and transferred to the right-hand side of the discretized equation. What we call pressure and denote with variable P usually contains contribution from bulk viscosity in the stress tensor and from the mean density in the gravity term. For this reason, the flow in a channel or pipe will have the same distribution of P irrespective of its orientation. If we need static pressure, we must subtract the other contributions if they are significant. In the differential form of momentum equations, the gradient of this quantity appears. See slide 5. If a finite difference method is used to solve the Navier-Stokes equations, this term can be approximated using any of the methods for the approximation of a first derivative described in lectures 4 and 5. Finite volume methods use the integral form of equations as the starting point. In the integral form of the Navier-Stokes equations, the pressure term can appear in two forms: a surface integral of pressure forces on control volume faces, or a volume integral of the pressure gradient. The former is a conservative approach, the latter is not. Depending on approximations used to discretize these two forms of pressure terms, the result may be the same or slightly different. The arrangement of variables on the grid is also important. This will be further discussed in slides 11 and 12. Body forces are usually specified as forces per unit volume. They are therefore in finite volume methods integrated over cell volume. Methods for volume integration described in lecture 7 and 8 can be used for this purpose. In most commercial codes, midpoint rule is used, that is, the source value at the cell center P is multiplied by the cell volume. If momentum equations are solved in non-Cartesian coordinate systems, additional source terms may result from coordinate transformations. For example, when two-dimensional axisymmetric problems are computed, the following source term appears in the equation for the radial velocity component. Note that this term can be treated implicitly because it contains the radial velocity at the cell center. It creates a positive contribution to the matrix coefficient AP because it is unconditionally negative on the right-hand side of equation. In the case of a swirling axisymmetric flow, more such terms are present. In any control volume, whether microscopic or macroscopic, the momentum is changed only by the flow through its surface, by forces acting on its surface, or by body forces. A finite volume method maintains these properties if pressure forces are computed in a conservative way, that is, as surface forces. Finite difference methods require special attention if conservation properties are to be maintained. In conservative methods, the sum of discretized momentum equations over all control volumes gives the conservation equation for the whole solution domain as a single volume, because all surface integrals over internal control volume faces cancel in such a sum out. Enforcing conservation of kinetic energy is also desirable, but there is no extra conservation equation for kinetic energy. It is derived by multiplying the momentum equation by velocity. Therefore, there is no obvious way of ensuring that kinetic energy is conserved by the velocity field obtained by solving discretized momentum equations. However, one should do numerical experiments to verify that the employed discretization method does not cause a growth of kinetic energy with time when it is physically not supposed to grow. One such numerical test will be presented in lectures 19 and 20. The simplest arrangement of variables on the grid is the so-called collocated arrangement, where all variables share the same grid node or control volume. This is illustrated for a two-dimensional case in the left figure for finite difference methods and in the right figure for finite volume methods. The advantages of this arrangement over all alternatives are simple bookkeeping in the computer code. There are less terms to compute because many parts are common for all variables. Application of boundary conditions is easier, especially in finite volume methods, because control volume boundaries can be arranged such that they coincide with edges or discontinuities in materials or boundary conditions. It is easier to implement multigrid methods because the same restriction and prolongation operators apply to all variables. And parallelization of the code is easier because all velocities can be exchanged between neighbor processors in one data transfer operation. The only disadvantage of this arrangement is that decoupling between velocities and pressure may occur unless special precautions are implemented, which is manifested in checkerboard oscillations. This will be addressed in lecture 18. Several staggered arrangements of variables on the grid have been proposed in literature. Figure on the left shows one partially staggered arrangement, while figure on the right shows the fully staggered arrangement on a two-dimensional Cartesian grid. Only the fully staggered approach will be described in detail in lecture 17. It has some advantages over collocated arrangement regarding pressure-velocity coupling when second-order methods, that is midpoint rule for integrals, central differences for gradients, are used on Cartesian grids. However, all topics listed as advantages of the collocated arrangement in the preceding slide are at the same time disadvantages of the fully staggered arrangement. Another disadvantage of the fully staggered arrangement is that it cannot be used on non-orthogonal grids unless they are structured and grid-oriented velocity components are used as variables. It is also not applicable on unstructured grids. These topics will be further discussed in lecture 1 of the second part of this course, CFD2. In each momentum equation, one velocity component dominates, ui, see slides 4 and 5. Obviously, momentum equations should be used to compute the velocities. Pressure features in each momentum equation, but there is no equation from which pressure could be computed in incompressible flows. The continuity equation is not a dynamic equation, but rather a kinematic constraint on the velocity field. It must be divergence-free in incompressible flows. Still, it is the only equation left to determine the pressure field. It is just not obvious how. If the velocity field must be divergence-free and the vector momentum equation is used to determine the velocity vector, it appears reasonable to apply the divergence operator to the momentum equation. Let us see what follows when this is done. We take the vector form of the momentum equation given here with this definition of the stress tensor. In incompressible flows, this part is zero, so only pressure and viscous stresses remain. The latter are proportional to the dynamic viscosity times rate of strain tensor. We now apply the divergence operator to this equation, that is, to each term on both sides. Some of the resulting terms are equal to 0 due to continuity equation. After some rearrangement, the following equation results. Here, S is the viscous part of the stress tensor because pressure was taken out of tensor T. In incompressible flows, S is equal to this part of the stress tensor. In Cartesian coordinates and tensor notation, the above equation look like this. This is the expression for viscous stresses in incompressible flows, corresponding to this part of the stress tensor T. When density, viscosity, and body forces are constant, the last equation from previous slide simplifies further by virtue of the continuity equation, leaving only one term on the right-hand side. If the velocity field is known, the pressure can be computed from this equation. This is a Poisson equation, but the Laplacian of pressure on the left-hand side is intentionally left split into an outer and an inner derivative. Note that the outer derivatives on both sides of the above pressure equation stem from applying the divergence operator to the momentum equation. For consistency reasons, they must be approximated in the same way on both sides of the equation. The inner derivatives on both sides stem from the momentum equation. They must be approximated in the same way as is done when discretizing the momentum equations. In general, computing pressure using the equation from the previous slide is not easy because we do not know the boundary conditions for pressure. This is why that equation is seldom used in CFD. It is more common to derive an equation for pressure correction using the same approach but discretized rather than differential equations. Most widely used are methods from the simple family. They derive a Poisson equation for pressure correction by imposing continuity constraint onto the velocity field obtained by solving the momentum equations with an estimated pressure and using a simplified relation between velocity correction and pressure correction. 4 methods from this family will be presented in lecture 18. Another class of methods for solving the Navier-Stokes equations are fractional step methods, which will be presented in lecture 17. There are many more methods in literature, but they all can be regarded as variants of one of the above approaches. All variables must be initialized prior to starting a simulation. For steady-state flows, initial values only affect the iteration process, that is, the number of iterations, computing time, etc. They do not affect the final solution. For unsteady flows, the initial solution must be a valid solution of the Navier-Stokes equation at time t equals 0. Errors in initial velocity and pressure fields affect the solution at many future time steps. If the flow is periodic, then the effect of initial conditions dies out after a few periods and does not affect future solutions. If the flow is stochastic, for example, turbulent flow simulated using direct or large eddy simulation approach, the effect of initial conditions also dies out after a while. Often, trivial solutions like constant velocity and pressure are specified as initial solutions, and we use larger time steps until the flow develops to a reasonable state. Boundary conditions must be applied at every time step. They may be constant or vary in time. At a wall, the no-slip condition applies. Fluid velocity at wall is equal to the wall velocity. In finite difference methods, this is the only condition imposed at a wall. In finite volume methods, another condition can be directly imposed at a solid wall. The normal viscous stress component is equal to 0 there by virtue of the continuity equation. Because the derivative of a wall parallel velocity component in the direction tangential to wall is equal to 0, the continuity equation requires that the derivative of wall normal velocity component in the direction normal to wall is also 0, resulting in a 0 normal viscous stress. This figure shows what the velocity profiles of the wall parallel and wall normal component look like near a wall. Therefore, the diffusion flux in the momentum equation for the wall normal velocity component must be 0. For example, at the south boundary. Setting only both velocity components at wall to 0, if wall is not moving, is not enough, because the discretized derivative of wall normal velocity component in the direction normal to wall may not come out as 0. Because we know that the normal viscous stress at the wall must be 0, we can specify that directly and do not have to evaluate the discretized approximation for it. To compute the shear stress at the wall, we only need an approximation of the gradient of wall parallel velocity component in wall normal direction. The derivative of wall normal velocity component in wall parallel direction is 0 because this component is constant at a solid wall, 0 if it is not moving. The simplest option is the assumption of a linear velocity variation, resulting in this approximation. Velocity at cell center minus velocity at wall divided by a distance. This is the case immediately at wall boundary in turbulent flows, but not in laminar flows. The next better option is the assumption of a quadratic variation, which leads to this approximation. If ghost nodes outside solution domain are used, the derivative at the wall face S can be computed in the same way as at the inner faces, for example using central difference approximation given here. The velocity components at the ghost node S must be computed so that the no-slip condition at wall is fulfilled. If a linear velocity profile is assumed, we obtain this expression. If a quadratic velocity profile is assumed, we obtained this expression. For higher order approximations, see lectures 6 and 9. At a symmetry plane, the shear stress is zero because the velocity component parallel to symmetry boundary has a zero gradient in the normal direction to the symmetry plane as shown in this figure. However, the velocity component normal to symmetry plane is equal to zero at the plane, no flow through symmetry plane, but its derivative in the direction normal to symmetry plane is not zero. If fluid decelerates along symmetry plane, for example, when approaching a stagnation point at an obstacle, the normal velocity component points away from symmetry plane. The opposite is true when fluid accelerates along symmetry plane. It then draws surrounding fluid toward the symmetry plane. For the situation shown in this figure, the diffusion flux in the U equation is zero, and the diffusion flux in the V equation requires an approximation of the derivative of V with respect to Y. The same approach as used to approximate the derivative of wall parallel component in the direction normal to wall can be used to approximate the derivative of boundary normal velocity component in the direction normal to boundary at the symmetry plane. Here is a brief summary of this lecture. Navier-Stokes equations have terms which are not present in the generic conservation equation and which require special attention. The additional diffusion terms cause no difficulties. Standard discretization principles apply, and their net effect is zero when fluid properties are constant. Pressure terms can be treated either as pressure forces on contour volume surface or as volumetric forces resulting from pressure gradient, corresponding to a conservative or non-conservative approach. The velocity components and pressure do not have to be stored at the same location on the grid. Staggered arrangements are also possible. Calculation of pressure in incompressible flows is a challenge. It must be derived via continuity equation, but the way is not obvious. A pressure equation can be derived, but boundary conditions for it are not available. Boundary conditions for momentum equations also require special attention, but this causes no difficulties.